In this video, we're going to look at the properties of waves, and the main idea of this section is that waves transfer energy without transferring matter. The essential questions we're going to answer are: what are waves? How do transverse and longitudinal waves compare? And what is the relationship between wave speed, wavelength, and frequency? Some vocabulary that we'll review is the term period, and some new terms may be wave, wave pulse, transverse wave, periodic wave, longitudinal wave, surface wave, trough, crest, wavelength, and frequency. So let's talk about mechanical waves. A wave is a disturbance that carries energy through a matter or space or some medium. And mechanical waves require this medium, such as water, air, ropes, spring, anything. If we don't have that medium, these waves actually cannot propagate. That medium is necessary to transfer this energy. And a wave pulse is a single bump or disturbance that travels through a medium. So this pulse right here, this is if just that pulse were traveling, that would be considered a wave pulse. Now what's pictured here is a series of pulses, and so this is a continuous wave. Or we often call this a periodic wave. So if the disturbances continue at a constant rate, then we call this a periodic wave because we're getting the same pulse every period. So there's two different types of mechanical waves. First is a transverse wave, and this is one that vibrates perpendicular to the direction of the wave motion. Light is considered a transverse wave. Think of holding a string here, and if you were to displace this string downward, it would send a pulse in two directions. It would send it out to the right and to the left. And that pulse, the movement of the string, is perpendicular to the movement of the wave. The wave is moving to the right, but the displacement is up and down. Whereas imagine a slinky and you squeeze a little portion of the slinky or stretch a little portion of the slinky and let it go, that's going to send that pulse to the right or to the left, and that pulse is just a compression of the slinky. So that means the displacement is left and right, whereas the movement of the wave is also left and right. That is called a longitudinal wave. So when we have a wave that vibrates perpendicular to the direction of the wave's motion, we call that a transverse wave. If we have one that vibrates parallel to the direction that the wave travels, then this is called a longitudinal wave. An example of that would be sound. Now let's think about the waves in, say, the ocean or the lake. What combination or which one is this type of wave? Is it a transverse or longitudinal? Well, waves that are deep in a lake or an ocean are in fact longitudinal, but at the surface of the water, however, the particles move in a direction that is both parallel and perpendicular. And so imagine yourself on this wave. You'll notice that you go up and down, and we may have all experienced this before, being in an ocean. When waves go towards you and through you, you rise up to the crest of the wave and you drop down to the trough. So you move up and down, but you're also moving back and forth. And so really your path traces out a circle. And so the wave is moving towards the shore, which is directed towards the right, but you're moving in a circular path. So it's a combination of both parallel to the wave motion and perpendicular. So it's a combination of longitudinal and transverse. But remember, deep in the lake or the ocean, the waves are in fact longitudinal. Each of the waves is called a surface wave, which has the characteristics of both transverse and longitudinal waves. Now let's talk about some wave properties. The amplitude of a periodic motion is the greatest distance from equilibrium. So when looking at the graph of a wave or this physical representation of a wave, this distance here from the crest to the equilibrium point or from the equilibrium point to the trough, that is the amplitude. the greatest distance away. Now we can notice right here, wave A and wave B, what's the difference in their amplitudes? Well, A has a greater amplitude because it goes higher than B does. A transverse wave's amplitude is the maximum distance of the wave from the equilibrium. And since amplitude is distance, we always consider it to be positive. And waves with greater amplitude transfer more energy. So higher the amplitude, higher the energy. Now we'll talk about sound more specifically later, but think of, greater amplitude, greater intensity. It's a louder sound. And for the waves that move at the same speed, the rate at which energy is transferred is proportional to the square of the amplitude. The key that you need to remember here is that when you double the amplitude of a wave, the amount of energy that the wave transfers increases by a factor of 4. So that's why it has this square relationship here. So we double the size of the wave, we make it twice as big. That requires 4 times as much energy. Continuing with some more wave properties, each low point of the wave is called the trough, and I've mentioned that already in the video. That's the low point here in the wave, whereas the high point is called the crest. The shortest distance between points where the wave pattern repeats is called the wavelength. So we're going crest to crest. That distance is the wavelength. Also, trough to trough, that distance is the same distance and is also the wavelength. We use the Greek letter lambda, lowercase lambda, to signify the wavelength. Crests are separated by one wavelength, and each trough are also separated by one wavelength. And if we want to find the speed at which the wave propagates, or the speed at which the wave is moving through the medium, we can take this crest-to-crest distance, or the trough-to-trough distance, and divide by the time that it takes. And so this just gives us our kinematic equation, the distance traveled divided by time, that will give us the speed. For most mechanical waves, except for the water surface waves, those are kind of screwy, the speed depends only on the medium through which the wave moves. So what this means is that sound is going to travel at a certain speed through air, and it's going to travel through a different speed through water, and it's going to travel in a different speed through wood. Okay, so these types of waves, they all depend upon the medium through which they travel. If you take a snapshot of the wave, you're able to see the whole wave at any one instant in time. And if we look at different particles along the wave, all the particles that are the same distance from the equilibrium point, we say that those are in phase with one another. So anytime we say that, this particle is in phase with another particle, that means they're the same distance away from the equilibrium point. Any 2 points on a wave that are one or more wavelengths apart are always in phase. For instance, this crest is one wavelength away from this crest, so they are the same distance away from the equilibrium. They are in phase. This point here is one wavelength away from this point over here, and so they are in phase with one another. Particles in a medium with opposite displacements and velocities are 180 degrees out of phase. So we have this idea of being in phase and out of phase. In phase of the same displacement from the equilibrium point. Out of phase, that's where either the particles in the medium are moving in the opposite direction or they have opposite displacements. Two particles in a wave can be anywhere from 0 to 180 degrees out of phase with one another. If you're 0 degrees, you're in phase, but any angle in between there, that's how we would describe either 30 degrees out of phase, 60 degrees out of phase. That's how much we have shifted either left or right with our waveform. If we were to look at one particle and the motion of one single particle on a wave and plot that motion in a displacement versus time graph, then we would see this wave function here pictured to the right, and we could find the period of its motion. And the period is the time it takes to get from one crest to the next crest, or from one trough to the next trough. It's the time it takes to complete one. The frequency, however, the frequency of a wave, which we use F to denote frequency, is the number of complete cycles or complete oscillations it makes every second. And the frequency and period are closely related. First off, we measure frequency in hertz, and we use Hz to signify that. And hertz are units per second. It's just 1 per second, 1 divided by a second. And this is talking about the number of cycles that we have per second when we use hertz. And the frequency and period are inversely related, meaning that the frequency is equal to the reciprocal of the period, or vice versa. The period is equal to the reciprocal of the frequency. So we use big T to denote period, little f to denote frequency, and they have an inverse relationship. Both the period and the frequency of a wave depend only on its source, what is creating this wave. They do not depend on the wave's speed or the medium through which it propagates. The wavelength, the wave speed, and the frequency, however, are related. And so we can relate the wavelength lambda, that is equal to the wave speed divided by the frequency. Let's look at a quick example using some of these equations. Let's say we have an 855 hertz disturbance, and remember this 855 hertz, that's telling us that it's going through 855 cycles every second. And this wave moves through an iron rail at a speed of 5,130 meters per second. So we're given the frequency f and we're given the speed v. We want to know what is the wavelength of the wave and what is the period of the wave. Well, let's look at what's the given information that we have, and we can list that out. And we just stated that we have the velocity and the frequency, and we're looking for lambda and t. Okay, so use our equations, and our two equations are v equals lambda f, and we can solve for lambda here to divide the velocity and the frequency to get 6 meters. So our wavelength is 6 meters. And then the relationship between frequency and period we know is an inverse relationship. And so that inverse relationship, we take the reciprocal of the frequency, 1 divided by 855, and so we get a period of 0.00117 seconds. So this is just over 1,000th of a second for one cycle to occur in this disturbance. So we can evaluate the answer. We see that we have meters for wavelength, we have seconds for period, and we're all good. Hopefully in this video you were able to answer these 3 essential questions and have a good idea of these vocabulary terms. Thank you.